Here, first of all, the question one is ABL tree range sum query. The problem statement is given an ABL tree storing numerical values. Design an algorithm to efficiently return the sum of all values within a given range L to R. The follow-up is how do you approach scale if each tree update must propagate features for downstream ML models. The core approach is the fundamental insight is to augment the ABL tree with additional metadata at each node to support efficient range queries. Instead of storing just the value and weight, each node would also maintain the sum of all values in its subtree. Each node keeps a running total of its inter-subtree's values. This augmentation allows us to answer range queries without visiting every node in the range. With subtree sums, anybody can skip traversing many nodes. Here is the core algorithm of this, and the algorithm works by leveraging the BST property during traversal. It can be used ordering of keys to guide the search. When we encounter a node during our range query, we make decision based on where the current node's value falls relative to our query range L to R. There is a real world example, and the real world example is at my previous company we used this exact approach for real-time analytics on user engagement scores. I applied this technique to engagement score data. We had millions of users with constantly updating engagement matrices, and marketing teams needed instant queries like give me some of engagement scores for user between 70 to 9 for targeted campaigns. So included here, there is also time complexity for this. Okay, and there is ML model updates, lazy propagation systems, mobile update strategies, and production architectures for this. Then the question 2 for this. The question 2 is mainly B-tree for large model weight storage, and this is mainly B-trees excel for large model weight storage due to their disk-friendly properties. B-trees are designed to minimize disk input-output. High fan-out. Each node can have hundreds of children, minimizing disk 6. Many children per node reduces tree depth and 6. Sequential access model weights often accessed in chunks. B-trees stores related data together. Related keys sit near and other things. Key design principles also here. Performance characteristics is also there, and also there is a real world example Uber's ML platform based. And key uses cases, production performance, also Netflix skills implementation is also given here, and optimization techniques is also given here. That from and the question 3 is distributed minimum spanning tree. In distributed minimum spanning tree, the problem statement is outline an algorithm for finding a minimum spanning tree and stay in a distributed system. In traditional MST algorithm, primes crystals don't work well in distributed settings. The Brubaker's algorithm can be effectively parallelized. Parallelized and phase-based approach is applied here, and it is explained here. and the detailed implementation is also shown here. There is a class distributed MST coordinator. Under there is a function, and all of these are applied here. The time complexity, iterations per iterations, and total. Real exemplification is a telecommunications network, and the problem context, Excel, objective constraints, and update frequency is also given here. The here implementation details, how it can be performed, result achieved, cost reduction, compute time, scalability, fault tolerance, and other things. Use case is smart agriculture IoT is given here. Algorithm for feature selection, some of algorithms, and production results is also given here. In additional benefits, MST enables efficient data aggregation, and there's benefits are given here. Other ML applications of MST like clustering validation, anomaly detection, feature engineering, dimensionality reduction, and network analysis. Then the number 4, memory management, slab allocation based garbage collection. The problem statement is for a tree or graph-based feature index in a memory constrained environment. Compare slab allocation-based garbage collection as memory management strategies. Follow up: which option better supports predictable latency for online serving and ML systems? So for this comprehensive analysis, memory management strategy critically impacts performance for tree or graph-based feature indicators. And then the slab allocation analysis advantages is given: predictable latency, cache efficiency, number of GC process, and other things. Disadvantages: memory overhead, manual management, complexity, and other things. And then given is garbage collection analysis advantages: automatic management, memory safety, flexible allocation, developer productivity, and other. Disadvantages: unpredictable process, memory overhead, throughput impact, and tuning complexity. Then good steps are given. Results comparison is given: GC implementation and slab implementation. And why slab allocation wins for ML serving? The reason is given. The reason is mainly the latency is predictable and bounded class, and real-time guarantees, financial trading, autonomous vehicles, real-time bidding, etc. is given here. So that's the part of this, and thank you.